Hey everybody, welcome back. Mr. Smith here. In today's slide deck, what we're going to do is to take a real step into the world of actual electronics, where things work in combination with each other. The most common elements that we study are resistors because they're the easiest thing to study, but they're not the only thing in circuits, as you'll see as we get into the lab work that we do. But I wanted to show you some series circuits and parallel circuits, get a little feel for what they look like, and show you some real live examples about how they operate as we begin. So to start with, this is a series circuit. The way you can tell that is that all three of these elements, or resistors, are in line with each other. So the battery down here exerts push, charges circulate, and you should notice right away that the charges that go through this resistor have to go through this resistor and this resistor before they make their way back to the battery. And that's what a series circuit is. It's all things in a line. So we've already looked at an example in the lab of a series circuit. We said that ammeters always need to be connected in series, and they can be hurt if they're not. Here's why. In a typical situation, let's say we have a 10 ohm lamp that's connected to, I don't know, a 30 volt battery. So current's going to flow through here. If I pop the ammeter in series, you might think, gosh, I need to make that ammeter not change the circuit that it's a part of, and that's why they work. The resistance of an ammeter is incredibly low. They might be 0.0001 ohms or even lower. The idea is that if I connect the two of these things together, I get 10 point something that's so small, the amount of current that actually will flow through from the battery won't be changed by the fact that an ammeter is sitting there. So what's a parallel circuit? A parallel circuit creates choices. So we have some wires down here, this one and this one, that connect to either side of the battery, and this group of wires. These wires, and I'll call them wire number 1 and wire number 2, they carry all of the current that comes out of the battery. These guys don't see all of the current. None of these resistors sees all the current. The way that they work is if this current number 1 were, say, 3 amps of current, this resistor might see 1 amp, this resistor might see 1 amp, and this one might see 1 amp. And the big thing you want to notice about parallel circuits is these 1, 2, 3 resistors, they act independently of each other. So a charge that flows out of the battery can choose at point A to go up, and if it chooses to go up, its circuit is going to run like that. It's going to run all the way around the top loop. If a charge chooses loop number 3 or resistor number 3, what it's going to do is follow a very different pathway. It's going to work this way back to the battery once it leaves point A. And so charges make a choice when they get to point A, and they rejoin at point B. So very different from a series. Where do you use a parallel circuit? Well, the most common kind we use all the time is the voltmeter. Now, the thing you need to know about a voltmeter is the voltmeter, if it's studying a 10 ohm resistor, the voltmeter has resistance of 10 million ohms or even higher, depending on how it's built. And the idea with a voltmeter is we create a choice by creating a parallel circuit situation. So if charges are flowing in this circuit around this way, they reach point A right here, and they make a choice. Almost all of them will choose to go through the 10 ohm resistor because the resistance of this one is so high, the current that chooses to go through the voltmeter will be very low, and it'll make overall, again, no difference to the function of the circuit. So that's how a voltmeter works, always in parallel. What's the big deal about the ammeter? Here it is. If you connect an ammeter wrong, and this letter V is an A, because you're taking our red boxy ammeter and you accidentally connect it in parallel, this would become 0.001 ohms in parallel. All the charges will choose to flow, not through the resistor at all. They'll choose to flow through your ammeter, and what you'll notice is the needle on the ammeter will swing hard to the right, and if you don't disconnect that thing right away, it'll twitch there for a second before you burn out the guts of the ammeter. So again, really important that you always connect an ammeter in series. Voltmeters, if you connect them wrong and you put them in series, they just kill the circuit. Not in a bad way, they just stop it from working because the resistance is so big, right? Okay, moving on. What I've got for you is now a simple series example that we're going to work through. What I've got here is a 60 volt battery, and I've got a number of resistors, and they made it easy on us. Each one of these is 10 ohms. And what I want you to notice about it is because this is a series and because all the current literally goes through all of those, what I could do is actually to collapse those resistors and draw them like they're one resistor, which leads us to the first rule of series circuits. What you should know is that the equivalent resistance of a series circuit is just what you get by adding up all the resistors. So if I take my 10 ohm, 10 ohm, 10 ohm, what I could do is literally redraw this simple circuit. And I'm going to flip my battery around just because I feel like it. I'm going to go and draw one 30 ohm resistor, and then here is my circuit. Charges will come out here, out the positive, scoot around the 30 ohms, and if I wanted to, I'll throw an ammeter in here, and we'll get to that in just a second and show you what that does, okay? But that's what it's going to look like. So now that I've redrawn the circuit, we come to our second rule, which is the current, as we talked about before, through each of these resistors has to be equal because they're in a series. So circuit current through 1 equals current through 2 equals the total current. What does the total current equal? We just use Ohm's law. So Ohm's law, it becomes a Swiss Army knife for us in solving circuit problems. What we do is we take the total voltage, which was 60 volts, and we look at our total resistance of 30 ohms, and all I do is take down here, current equals total voltage of 60 volts divided by 30 ohms, and we get that the total current through this guy is 2 amps. So we have 2 amps of current flowing through each one of those resistors. Okay, so that's how we use, in a very, very easy problem, simple series circuit, to use Ohm's law. Next thing we're going to do with it is we realize that the total voltage, our 60 volts, is the sum of all the voltage drops. So voltage is energy, and what we do is we notice that the charges are going to lose some energy on each one of these things in a series because they're in a series. So what I'm going to do here is a tactic you'll see me often do. I'm going to leave aside my redrawn example because I don't need it anymore, but I'm going to draw a voltmeter around that first resistor. And we're going to use Ohm's law right now and apply it just to this resistor. I know for a fact from before that the last step, that there's 2 amps of current flowing through this resistor. So this resistor, all of them get 2 amps. So what's this voltmeter going to read up here? Well, it's not hard to figure out. What you're going to do is to say the voltage equals I times R for that resistor. So 2 amps go through it. The resistance of it is 10 ohms. And what we figure out is that I have 20 volts of voltage loss on this resistor. So this guy right here is going to say 20V. Because they're all identical, we made this easy. This one's going to read 20 volts. This one's going to read 20 volts. But that's how you're going to work through a simple series circuit. You collapse it, and then you expand it again and use Ohm's law a couple of times. So what's a actual real-life example of how series circuits operate in everyday life? Batteries are a very common example of a series. The way that they work is that batteries in real life do have some actual resistance to the flow of charge. It has to do with how they're built and also their age. As they age, the resistance goes up. So you might think about the fact that if I have a battery that says it's a 9-volt battery, if this resistor, if we imagine a resistor living inside of the battery, if current goes through this, there's going to be a voltage drop on it. And that would be this. This curly E would be our 9 volts. So let's show you an actual example of how this works. What we're going to do is take a 6-volt old Game Boy battery, and this is a realistic number. It has a resistance internally of 1 ohm, and the game draws current. Well, here's the deal. The curly E stands for EMF. So that's what's called the nominal voltage of a battery. That's going to be 6 volts. That's what the battery will read if you touch it with a voltmeter from our lab. It'll tell you I'm a 6-volt battery. In real life, we don't know that that means that this battery can actually deliver 6 volts. Well, what will it really deliver? It depends on how much we ask of it. So what I do is I use the rest of this equation in this simple example. 6 volts minus I, so I is 0.45 amps, and we multiply then by the resistance of the battery. And what we're going to end up with here is when we do our subtraction, we're going to end up with the fact that this Game Boy battery isn't going to deliver 6 volts. The VAB, the actual battery voltage that it can deliver when it's being asked to do this much current, is going to be 5.5 volts or so. Is it a big deal? I don't know. It depends. It might be in some situations. Here's a different version of that same example, and we're going to use our series circuit skills to look at this one. So this happens in your car. Your car can supply as much, maybe as 600 amps, some batteries, but a battery might be rated at 12 volts for 450 amps. That's a lot of current because batteries are a really serious device in a car. The battery would have a really, really low resistance. So what's the actual voltage, the terminal voltage that the battery will generate when we connect it to a 100 ohm load? To get this, what you have to do is to realize that I've got to draw a circuit. I've got a battery that's 12 volts. That's the EMF, the nominal voltage. Then what I've got is, in this first example, 100 ohms attached to my little battery resistor of 0.01 ohms. And what I'm going to do is throw an ammeter out on our circuit diagram and use the skills that we just developed in studying series circuits. What's the first step? Add these resistors together. So the R equivalent for my network of resistors that are in series is 100.01 ohms. Okay? The next step that we do is we use Ohm's law and our R equivalent. So I equals V divided by R. And so what I'm thinking of now is the equivalent resistance. In my mind, what I've done is I've redrawn this and collapsed these into one resistor. So my voltage is 12 volts. I divide that by 100.01 ohms. And as you imagine, the 0.01 doesn't make any difference on this. It's a rounding error on how this number works. So the amp current comes out to be 0.12 of an amp. Okay, so finally, what's the voltage AB that we generate from this? Well, it's just going to be 12 volts minus 0.01 ohms times this very small current. Well, not very small, but it's not terribly huge, not compared to what the battery can do. And what we're going to get is a very small answer. So the VAB, when I'm all done, I worked myself out of room here, is going to be essentially 12 volts. Okay, this really doesn't make any difference. But when we connect it to something like the starting motor of the car, let's go and see what happens. The starting motor might have an incredibly low resistance because the starting motor really draws a lot of current. Let's go check it out. So same example. What I'm going to do is just work through my steps. The R equivalent, if I don't bother to redraw this circuit, is going to be 0.03 of an ohm. And so what I'm going to do is go and get the I equals 12 volts over the equivalent resistance, 0.03 of an ohm, and that is a lot of current. So I get 400 amps coming out of my battery. So what's the deal? Well, the voltage that I'm actually going to see from the battery is going to be 12 volts minus 0.01 of an ohm. That's the internal resistance of the battery, times that 400 amps. So because the current is so big, that actually makes a significant difference. So my battery is only going to be able to produce to the motor 8 volts of push, or 8 volts of EMF. And that's a real problem. So that's why in the cold weather, when resistance of the battery is higher chemically, you get more difficulty starting your car. So anyway, those are some basics. Bring your questions to class. Looking forward to seeing you. Take care. Bye-bye.